One of the tests using the chi-square distribution is a test of independence of two variables. For example, a professor claims that students' teacher ratings depend on the grades students receive. To test this claim, the student assembly took a random sample of 300 teacher ratings on which the students' grades for the course also were indicated. Test the hypothesis that teacher ratings and student grades are independent at the 1% significance level. So we see the results in the table. Excellent, average, and poor, and the grades A, B, C, and F. And these numbers in here are the frequencies of each that have occurred. So we'll begin by stating the hypotheses. The null hypothesis is that teacher ratings and student grades are independent. In other words, the ratings teachers get are not dependent on the grades the student receives. The alternative hypothesis would be that teacher ratings are dependent on student grades. So we need to calculate the chi-square statistic. Before we can do that, we need to calculate the expected frequencies for each one of these. Expected frequency is calculated by multiplying the row total times the column total and dividing by n, the total number of observations there are. So let's first calculate each of the row totals and each of the column totals. So for the first row, under the category excellent, the row total is the sum of all of these frequencies, 14 plus 18 plus 15 plus 3. That gives us a row total of 50. The second row, we total these four numbers, and that gives us a row total of 150. And for the third row, we get a row total of 100. If we total each column, so the column under A, 14 plus 25 plus 21 gives us a column total of 60. 18 plus 35 plus 27 gives us a column total of 80. 15 plus 75 plus 40 gives us a column total of 130. And 3 plus 15 plus 12 gives us a column total of 30. So we have to actually go through and calculate the expected frequency for each. This will allow us to compute the chi-square statistic. The chi-square statistic is calculated by taking the sum of each observed frequency minus its expected frequency squared divided by the expected frequency of that observation. So it's probably best if we organize this in a table. We'll make the first column the observed frequency. The second column will be our expected frequency. And then the third column will be this expression, observed frequency minus expected frequency squared divided by expected frequency. This expression here is also known as the residual or the Pearson residual. So let's start with the observation of 14. So we'll record that number under the observed frequency. Now the expected frequency for this column or for this observation will be the row total, 50, this is the row in which 14 falls under. So since it falls under the row where the total was 50, the row total for that observation is 50. The column total under 14, or under the column A here, is 60. So the expected frequency is 50 times 60 divided by n. This is told to us in the problem, 300. If it weren't, we could simply add up all these numbers or add up just the row totals or just the column totals. So we have 50 divided by times 60 divided by 300. This gives us an expected frequency here of 10. We can calculate now the residual for this. So the residual is calculated by doing the observed minus the expected, so 14 minus 10, squared divided by the expected, which is 10. This can be done in all-in-one calculation. Just be very careful with parentheses. You have to put parentheses around the 14 minus 10 before you square it. So when we do 14 minus 10 squared divided by 10, that gives us a residual of 1.6. So if we move across, we can go to 18. The order in which you do these is not important because you're going to add. So whatever makes the most sense to you is fine. So the expected frequency here is the row total. This is under the same row as the previous one, so the row total is still 50. Now the column total, this is under column B, so the column total is 80 divided by 300. This gives us an expected frequency that's 13.3 repeating, so we can round this to 13. Again, this is a non-terminating decimal, so round enough so that you won't have errors with your rounding. So we have the expected frequency here as 13.33333. Now again, we're going to calculate the residual, so it will be 18 minus 13.33333 squared divided by 13.33333. And again, we're going to have to round this, so we use enough decimal places that we won't have too many errors due to rounding. If we take 15 as the next observed frequency, again, we calculate the expected frequency here. This is again under the same row. The row total is 50. This column total now is 130. So we have 50 times 130 divided by 300. And this gives us an expected frequency, again, that we have to round, 21.6 repeating. So we can round that. So again, the residual here will be 15 minus 21.66667 squared, again, divided by the expected frequency, so 21.66667. Again, we'll have to round this, so this is 2.05128. Again, this can be done in one calculation, but please be careful with parentheses. Our last entry in this row is 3. So we still have a row total of 50, but now 3 falls under the column total of 30. So we have, for the expected frequency, 50 times 30 divided by 300. So that gives us an expected frequency of 5. When we calculate the residual here, we have 3 minus 5 squared divided by 5, and that gives us a nice residual of 0.8. Now we're moving into our next row. So we can look at 25 as our next observed frequency. So 25, and we now have to compute the expected frequency here. So now this is under the row total of 150. So we have 150. The column this falls under is 60 because this is in the column A. So we have 150 times 60 divided by 300. So this gives us an expected frequency of 30. So we can calculate the residual here, 25 minus 30 squared divided by 30. And that gives us approximately 0.83333. Again, it's 0.83 repeating, so we can round that. So our next observed frequency is 35. And again, we'll calculate the expected frequency here. The row total is still 150. The column total is 80. So we have 150 times 80 divided by 300. This gives us an expected frequency of 40. So we have a residual of 35 minus 40 squared divided by 40, and that gives us 0.625. Moving to our next observation, we have 75. 75 falls under the row of 150, the row total of 150, and the column total of 130. So we have an expected frequency here of 150 times 130 divided by 300. So we get an expected frequency here of 65. Our residual is 75 minus 65 squared divided by 65. And we get here approximately 1.53846. Our next observation is 15. Again, we're going to calculate the expected frequency here. So we're still under the row total of 150, but now we're under the column total of 30. So we have 150 times 30 divided by 300, and this actually gives us an expected frequency of 15. So there's not much to calculate here for the residual because the observed minus the expected is 0. So squaring it and dividing by the expected will still give you a residual here of 0. Moving to our last row, our next observed frequency is 21. So again, we're going to use the row total. This is now 100, and our column total is 60. So we have 100 times 60 divided by 300, and this gives us an expected frequency of 20. So our residual here is 21 minus 20 squared divided by 20, and this gives us 0.05. The next observed frequency is 27. The row total here is 100. The column total is 80. So here we have 100 times 80 divided by 300. And that gives us an expected frequency of 26.6 repeating. And we get a residual of 27 minus 26.66667 squared divided by 26.66667 for approximately 0.004167. Next, we have 40 with the row total of 100 and a column total of 130. So we have row total 100, column total 130. Divided by 300. So we get here about 43.3 repeating, with the residual 40 minus 43.33333 squared divided by 43.33333. This gives us a residual of about 0.25641. And finally, our last observed frequency is 12. For the expected frequency here, we have a row total of 100, a column total of 30. So this is 100 times 30 divided by 300. This gives us an expected frequency here of 10. 12 minus 10 squared divided by 10 gives us a residual of 0.4. So we're now ready to compute the chi-square statistic. If we go back to the formula for the chi-square statistic, we can see that this is simply just the sum of each one of the residuals. So all we have to do to compute the chi-square statistic is total this last column here. So we have 12 values to total, but if we add each one of these, starting with 1.6 all the way down through 0.4, we end up with a chi-square statistic of about 9.792. So this is our chi-square statistic, but we still have to conclude our test and figure out if these variables actually are independent. So with the chi-square statistic of 9.792, we need to pair this now with the degrees of freedom. Degrees of freedom for a test of independence can be written like this, where R is the number of rows and C is the number of columns. So this is number of rows minus 1 times number of columns minus 1. If we go back to our original contingency table, we can see here that the number of rows is 3. Remember, rows are always across. We knew this by saying that this was the row total. Since we have 3 row totals, it makes sense that we have 3 rows. The columns, there are 4. So we have a total of 3 rows and 4 columns. So this gives us degrees of freedom 3 minus 1 times 4 minus 1. So 2 times 3, which is 6. So we also want to note in the original problem here, we're told to test this at a 1% significance level. So this is alpha. Alpha is 1%. So just by looking up on a table, we won't be able to find an exact p-value, but we will be able to find an interval for the p-value that should give us enough information as to whether or not we should reject or not reject the null hypothesis. So if we look at a chi-square table, we're looking under degrees of freedom 6, and what we're technically looking for is the chi-square statistic of 9.792. So if we go down this line, we can see we don't see that. There is a pretty large gap in here where 9.792 lies. And if we look at the corresponding right tail area, it is a pretty large interval. This is okay because this is still enough information that for us to be able to actually conclude our test. What we found out is because 9.792 lies between 0.100 and 0.900, then the p-value is somewhere between those two numbers, 0.1 and 0.9. So again, this is a very large interval, somewhere between 10% and 90%. However, this is still enough for us to conclude this test. So we know that our p-value is somewhere in the interval from 0.1 to 0.9. Again, very large interval, but this is okay because we know alpha is 1%, which is 0.01. So when we compare this, if the p-value is somewhere between 0.1 and 0.9, we can look at it this way and say, if it's greater than 0.1, then it is definitely much greater than 0.01. So because the p-value is greater than the significance level of alpha, this leads us to a conclusion to not reject the null hypothesis. So we can conclude and say there is insufficient evidence at the 1% significance level to support the claim, to support the professor's claim that teacher ratings are dependent on grades. Now, if we want to actually calculate a p-value, we can't really do this by just using a table. However, we can use other resources like a p-value calculator. Just by Googling p-value calculator, you can come up with a lot of options. Here, this is specifically a p-value calculator for a chi-square statistic. So we can enter here our chi-square score and our degrees of freedom. You can even enter the significance level here. There's only 3 options, but one of ours is on here, 0.01, and calculate. So we can see here that the p-value is 0.133689, and it even tells you here that the results are not significant, which is what we concluded. So we have a better actual approximation here of the p-value, especially considering here our interval was so large between 0.1 and 0.9. This 0.13 approximation makes sense, as 9.792 we can see is closer to 10.64, so it would mean that the p-value should be a little bit closer to 0.1 than it was to 0.9. Again, even with such a large interval here though, we can still gather enough information to know whether or not we should reject or not reject the null hypothesis. So we really don't need this p-value calculator for what we're doing here, but it is interesting to note that we can find it. So again, because we figured out that our p-value, again, even here if we're using this large interval, it doesn't really matter that we don't know what p is between 0.1 and 0.9. We still know that if it's greater than 0.1, then it definitely must be greater than 0.01, which is our significance level. So again, we are not rejecting the null hypothesis. Our null hypothesis, recall, was that teacher ratings and student grades are independent. We're not rejecting that, so we're saying here that we don't have enough evidence to support this claim, which is the teacher's claim.